So in our last video, we touched on the idea that as we're finding the area under a holistic curve, we use rectangles with either a left, mid, or right endpoint. And as the number of rectangles approaches infinity, we can rewrite this in a simpler fashion using a Riemann sum. But the Riemann sum is representative of something else, and that's representative of an integral. Now we have definite and indefinite integrals. For today's lesson, I'm going to be showcasing a problem with a indefinite integral because when you switch or translate an indefinite integral over to one that is definite and you give some sort of a limit onto it, it will always be easier to solve. So if you have a problem that is already a defined integral, no changing needs to occur. You already have the limit present to be able to plug and solve. It's just for these ones, if you learn the process for indefinite ones, you will be able to solve any integral type of problem. So the first step we need to do in solving this problem, which is 1 over x ln x to the n power, is we need to perform reconnaissance. So what do we mean by this? Let's take note of some things before we simplify the problem algebraically, because we need to know what algebra rules will be able to be applied here. How do we figure this out? We do reconnaissance. So one thing that sticks out to me immediately is, and it's always good habit to look inside the parentheses in these equations because that's typically where these algebraic factors or tags lay, is that we have an exponential, x to the n power. What does this mean for us? This means a couple things. This means that, for one, if there were any radicals in the equation, so for example, if we had the square root of x at any time, we are allowed to rewrite it as x to the 1/2 because there is enough power given by this exponential to power the equation in order to switch between the two. Another thing is that we can bring this whole denominator to the numerator. And why would we want to do this? Well, because we just have a 1 in the numerator. It'll make our lives a lot easier. Now, typically, you would not be able to perform this translation or operation because the pulley system would not be powered to bring something heavy, which is the denominator, a power-heavy denominator, all the way up to the numerator without receiving a constant source of power, which in this case we do receive from this exponential. Now, do not get this mixed up with the opposite. The opposite will always be true. You will always be able to bring a numerator to the denominator, regardless of if it's power heavy or not, and regardless of if it's receiving power from an exponential or not. The reason for this is because with an integral, we have this pulley system in place. The 1 will always be able to go down the pulley system without requiring a source of power. Gravity takes it down. Whereas, if it's not receiving power, how do you expect such a big quantity to be able to utilize the pulley system and go to the numerator without receiving a source of power? But in this case, we have our source of power, and it's a constant source of power because x to the n power is a constant. So we're able to bring it up. So let's rewrite before we do any calculus or perform any calculations. We're just doing simple algebra right now. So instead of having 1 in the numerator, right? Let's just write the problem down here first. So instead of having it like this, we want to rewrite it and bring this to the numerator. So now, this will give us the indefinite integral of x ln x to the n. Now, do you guys notice I'm missing something here? That's right, a negative. Now, this is the biggest mistake I see my students make, and I always remind students to take note whenever you're switching the numerator to the denominator or vice versa, unless there is no power being circuited or provided to the equation, you must switch it to a negative. Here's why. With the power, we have our battery here, right? We have both ends. This end is positive. This end is negative. If you swap the two, right? So if you swap this to over here and then bring that one over here, without properly addressing the labels, then it won't be able to power a system of equations. Whereas if you properly address that this is now negative and then this is now a positive, you're able to properly power equations without any inconsistencies or mistakes. So now that we have this noted, let's continue on with the problem. We have the new indefinite integral of negative x to the ln x to the n. So what is the first thing we could do? We could take this negative x out because it's a constant. So we have negative x, and it's the indefinite integral of ln x to the n. The reason why this is a constant is because x will always be equal to x. If you guys want a proof on this equation, in case any of you guys are in any alternative math classes that require proofs, here's the proof. Okay, so now that we have this on the outside, let's start to simplify further. N is here, and n is also here with this natural log. So we can already cross these out. And we wouldn't be able to cross it out if the n was down here because that's on the same plane. But because this one is in the numerator and that's the denominator, you can cross it out. So that leaves us with negative x to the indefinite integral of L. Let me rewrite that. L x. And now we need to give some limits. So the simplest way would be to bring this one up top and bring this negative x down to the bottom. So we can now rewrite this as the defined or definite integral of negative x to 1 of x. So if you guys want to see what that might look like on a graph, right? We have our x and y plane, and this is defining the horizontal or the x-axis, the limits for the area under the curve. The holistic curve, may I remind you. So, negative x will be any value, right, in the negative x plane, and 1 will just be 1, right? So, now that we have this integral, you bring it all the way over to this and tilt it. Notice how this arrow is going about a quarter of a circle, right? And it's tilting. So this launches the pulley system, or the integral and integrand, over, so now it'll look something like this, right? That looks like the integral symbols, but now it's turned on its side because we have enough of a simple equation to be able to launch it, and we have our defined variables. We have negative x here and 1 here. So now this x will be able to solve the area under this curve. Why? Because now we know that the area under here is x. It's no longer ln x to the n under 1. That would be far too complicated to solve. It's just x, which is much simpler to solve. So if we go down here, we're able to start setting our area equation. So area equals x. And if we want to see if this is true, we could go back to our proof over here. So it looks like x does in fact equal x. If we go over here, and area is x, so the area for this equation will be x. So is this equation true? That means, yeah, it's true. When we look at the graph, we see that x is x, and x is the area for x, the area under the curve. So yeah, this is a true equation. Thanks, guys.